Hello everyone, let's start. Today we will talk about mask and decoder in the first half of this lecture. In the second half of this lecture, we will talk about some reconfigurable logic. So I would like to use one example to explain the masks and the decoders. So here is a LED light. It has 7 pieces. So we have A, B, C, D to, I'm sorry, 8. We still have a dot here. We have 8 pieces. Assume that this light is controlled by 8 enable signals. Each enable can control one a portion of the light. For example, the A part. If the enable signal is enabled, then you can see some light. Otherwise, it's just black. So it's something like this. In this way, we need a chip. A chip can, for example, if you send a chip is actually a translator, which can translate your input signal to the control enable signal of the lights. For example, you can send a 7 here through the this chip, and then this light exactly give you a 7 like this. So this light is controlled by 8 signals here. Here are 7 signals. We still need some control signal to control this DP. We need 7 or 8 enable control signals, and we have 4 bits here. These 4 bits are the binary representation of your input, because we only have one LED light, which can represent from 0 to 9. So 4 bits are totally enough because we have 10 numbers. If you want to, display this 7, you can send this 0, 1, 1, 1, which is the binary representation of the number. So we can have something like this from 0 to 9. So these are 10 numbers. The next step is to draw a truth table. And we would like to understand when do we need to turn on the segment of E? When do we need to turn on this one? So for the E is our output. We have 4 inputs. E is our output. Let's draw this truth table. Because we have 4 inputs, totally we have how many rows? 2 to 4, 16 rows here. And then we can check which one can give you which one will turn on this part. 0, yes, we have we have 1 here, because for the 0 we turn on this part. 1, no. 2, yes, so 2 also have a 1. 3, no. 4, no. 5, no. 6, yes. This one is the 6th part. And this is the 6th case. 7, no. 8, yes, this is 8. 9, no. So this is 0. So in this way, we can finish the truth table for output E. And these rows, we don't care about them. Because for the chip, if we design a chip, we only need to translate from 0 to 9. If you cannot give me 11, so we do not care about these rows. So we just write do not care signal. When we study the K-map, we know what do not care mean. And in this way, we can draw a K-map. We have 4 inputs here. So we have a 0, 0. This is D0, D1, 0, 0, 0, 1. We don't have 1, 0 here. We have a 1, 1. Please notice that. And this is 1, 0. For the connecting neighboring columns, only 1 bit can be changed. So from here to here, from this row to, from this column to this column, only the first bit is changed. So in this way, we can, put these ones into this K-map and try to draw as large as possible. So we can have a group like this. So in this way, we can, have the representation of E. We can build this E by 1 AND gate, 2 AND gate, 3 AND gate, 3 AND gate, and a OR gate. So in this way, we can, output the correct E by the inputs. Of course, you need to design a controller for G, D, C, B, F, and A separately. But in this particular example, I only do this for the E. Another example is a selector. For example, we have 2 inputs here. And by a control signal, we can select 1 between A and B. So if I set S is 0, then the output is A. If I set S is 1, then the output equals B. Because here we have 3 input signals, so we have a 2, 2, 3, which is 8 rows, and then we can draw the truth table, and use K-map, do the simplification. We get this one. This is a typical masks. This is a typical mask. You can select, one signal between multiple signals by one or multiple control signals. So the 2-to-1 mask is the name of this piece of circuit. It's the most important unit which you can use in memory arrays. If we further break it into multiple logic gates, you can use this circuit to implement this 2-to-1 mask. So by the first example, we explained the decoder. The decoder can be very complicated, just like the decoder we introduced in the LET light. In the second example, we talk about a mask. Mask is, compared to the decoder, is relatively simpler. We have only one 2-to-1 mask. The function of a decoder is actually when you put a number here, input number here, the corresponding row will be enabled. For example, this is a 3 to 8 decoder. if you input 0, 1, 1 here, this is actually a 3. Then the T3 will be enabled. So this is the function of the 3 to 8 decoder. And we can also draw a truth table here. The OEB is a reset signal. And we didn't show this reset signal here. When the reset signal is 1, then all the output are zeros. So this part of the truth table is the real function of the 3 to 8 decoder. So you can see that in each row, only one output signal is enabled. By this truth table, you can also use some AND OR gate to implement this. So this is the 3 to 8 decoder implemented by NOT gate and OR gate. I'm sorry, AND gate. So we can have multiple types of address decoder and multiplier, like 2 to 1, 4 to 1, 8 to 1. So basically, the function of the decoder is the inverse function of multiplier. So I'm sorry, not multiplier, but a mux. So for the mux, the function of a mux is select one signal among multiple one. But the function of decoder is to decode the value of your one single input to select one output. Any question about this? So the decoder and the encoder are heavily, I'm sorry, the decoder and the masks are heavily implemented in memory arrays. So when we will talk about memory arrays in the future lectures. When we do that, we will review this decoder and the masks again. The next topic is programmable logic, some reconfigurable or programmable logic. These are some early stage of the modern FPGA. We will also talk about FPGA in the next lecture. But in this lecture, let's review the prototype of the modern FPGA, some basics of the modern FPGA. So how the people build a basic of FPGA in this lecture. The most important unit is the trace state buffer. This is one example of the trace state buffer. This is a truth table. For the triple state buffer, it has two inputs, A and B. It has only one output. So when B is the control signal is a 0, the output is some unstable signal, and it's not a 1 or 0. So it's not stable. We cannot use this signal. But when the B is 1, then the output is output C is equals to the input A. So you can see these two are the same, and these two are the same. And this is one example of the connection, reconfigurable connection. So when you close this switch, these two lines are connected together. If you open this switch, then they are not connected. So this is the programmable logic example. In this programmable logic example, we have NOT gates, we have AND gates, we also have some OR gates. So you can review this part. This part is actually a so-called decoder. So it's a different from decoder because for the decoder, these are the AND gate. And here are also some AND gate, but you have more connections here. And these connections are reconfigurable. So you can see the comparison between this figure and this figure. So in this figure, we have all the connections here. But actually, you can open that switch and only leave several of them connected. So in this way, you can actually configure the logic here. For example, for this row, if you only want to have A and B, you just keep this signal and this signal closed. This switch and this switch closed. So that this line can be connected to here and this line can be connected to here. So in this way, you can have A and B. But in this period figure, this is a full functional decoder, and you have all these connections. But you can control this dynamically. So, for example, for this row, if you want to have a B bar and C, so you keep this part closed and keep this part closed. Based on the value of each row here, you can adjust the switch in this part. When you have the signal you want at each row, you can also control the switch here so that you just keep the switch closed if you want to have a OR signal here. For example, for this OR gate, it's an OR operation between this part and this part. So basically, by controlling the switches here and the switches here, you can actually program the function of this unit. So we can also use this signal to represent a switch. So if we have these signals here, it means the switch is closed. In this particular example, let's calculate the function of each part here. Because we have a switch here and a switch closed here, closed switch here and closed switch here, we have A and B. So this is the signal of the row. We have a closed signal here, a closed switch here, and we also have a closed switch here. For this OR gate, we have A, B, or A bar, and B bar. So this is the output here. For this one, this one is actually a XNOR gate. And this one is actually this part is a XOR gate. So by this piece of programmable circuit, we can program and or XOR multiple functions by this one single piece of unit. So here is another example. So we have 3 inputs signal and 2 output signal. So how to use this piece of circuit to implement Z1 and Z0? So the first step is to write the canonical form of Z1 and Z0. So these are the canonical form. These are so-called sum of the miniterm or sum of the product. When we have these canonical form, we can implement Z1 and Z0 by this piece of circuit. So this is the implementation. So for the rows here, we need to implement this miniterms, these miniterms. For example, to implement this part, x0, x1 bar, and x2 bar, we need to have a Z0 closed, this switch closed. When this switch is closed, we can have x0, so like this. And then we have x1 bar. So this is, because this is NOR gate, so we have x1 bar. And then we have x2 bar, because this is a NOT gate. So by this line, we can implement this one, this miniterm. We can also do the do the implementation for this term here. This is x0, this is x1, and this is x2 bar, which is exactly this minterm. So by this part, we can implement all the minterm here. And by these OR gate, we can configure them like this. I'm sorry, this is an AND gate. By this OR gate, we can configure the switches here so that we can have these 2 OR operation here. So by close these 3 switches, we can implement Z1 here. By close these 2, we can implement Z0 here. So this is the so-called prototype of a reconfigurable logic, which is also the prototype of the FPGA. But for the real FPGA, we have more complex connections. And this one is actually a complex version of this one. So you can see we have a lot of inputs here. We have a lot of AND gate and OR gates here. We also have some, this is so-called latch. D latch can temporarily store the output of this OR gate. So this one is actually the so-called CB, the configurable block in a FPGA. So we also have the signal here. So by this clock signal, we can configure this CB into different functions. So in this particular, for example, in this cycle A or cycle 1, we configure this part as an AND gate. For cycle 2, we can reconfigure it into a AND gate. So in this way, we can reuse this CB. And this one is actually the CB. It's also called a logic block or config block. And to implement a more complex function, we need some reconfigurable switches here and I/O blocks here. And this is the details inside one switch. For example, this is cross point of the switch. This is also the cross point of switch. For the switch, we also have a SRAM cell here. We can write 0 and 1 into this SRAM. By programming this SRAM, we can control this switch closed or open. So it's also a switch. We can close it and open it. In this way, we can connect the function in this logic cell or CB. We can connect this CB to this CB, or we can also disconnect them. So in this way, we can use these logic cells to build a more complex function by writing different value to these SRAMs. So because the SRAM is a very power consuming and it also costs a large chip area. So the connections here, these connections are actually even larger than these logic cells. Because in the logic cell, you just have some AND gates, OR gates, and some D-latch. They are very dense. But in the reconfigurable interconnections, they have some SRAM. So the area of these interconnections may not be smaller than these logic cells. They also these interconnections also consume a very substantial portion of the power. So these are the example of the FPGAs. So in FPGA, we have some LED lights. We have the FPGA chips. The FPGA have a different topology. So this is only one type of a topology. We have a so-called multiple logic cells here and use the interconnection, reconfigurable interconnection to connect them. We can also have a so-called centralized FPGA architecture, which means that in the middle of the FPGA chip, we have all the connections here. But you know, in the top, in the bottom, and we have some generic logic blocks. So we can put the logic blocks around these interconnections. So this type of FPGA can give you more flexible, reconfigurable capability because they have a lot of connections here. So we can use this type of FPGA architecture to implement some more complex functions. In the next lecture, we will talk about more on the FPGA architecture. These are some very basic elementary introduction to the FPGA. Any questions? We can also have the office hour now. If you have any question about homework or about the project, you can ask me now.
Hello, can you hear me?
Yes.
Yeah, I said one question about the project. Are we just going to be simulating this, or are we going to write it to an FPGA board?
I have so I actually have some FPGA board, if you are interested in downloading your bit stream, so after you do the debugging simulation, you can actually compile it or synthesize it into some bit stream. If you are interested in downloading your bit stream into some real FPGA, you can contact me so that I can give you some balls. We can also try to utilize the cloud-based FPGA. You know that Amazon provides some AWS FPGA. We can talk about that.
Okay, thank you.
So I update the reading list in our canvas. You can access the reading list by this link. In the reading list, I post the reference of the deep learning talk I provided in previous lecture. For example, we have the binary connection. Quantize the weight into 1 and -1. This is that reference, binary connection. XOR-NET, which quantize both the input and the weights into 1 and -1 so that you can do XNOR and pop counting for the inference. We also have the shift CNN. You do shift and add. Please read these references so that you can choose a application to do the acceleration. For example, if you want to implement this for your project, that will be great. I put a lot of also some other reference. For example, the BERT, QBERT. BERT is a network architecture which I didn't mention in my talk. It's about the machine translation, language processing. We can also try to accelerate these applications. So I will schedule a time slot for everyone here so that you can present the proposal of your projects. I will post the requirement of your project in this week so that you can find a group mate. You can find another student to work with you to do the project. So I will give you some example. For example, if you want to accelerate this XOR-NET, one student can run the GPU code so that it can generate some data. The other students can do the XOR and pop counting logic implementation. So eventually you two can compare your results, validate a result against each other. Of course, in order to do that, when you write some Python code on GPU, you should not only print out the final result, but also the intermediate result for the debugging of the VHDL. So in this way, you can form a group and finish the project. And in the reading list, I just give you several examples like a binary connection, XOR-NET, and shift-CNN as the project examples. You can also propose your own topic. You can also work along. But I would like to limit the size of each group under 3. So 1 or 2 students is should be good for one group. Any question?
I'm sorry, I think I missed it. What are we presenting in those time slots? Just our original choice of project?
The topic, for example, if you want to accelerate this one, you need to introduce some basics of the XOR-NET. So for example, what's the major operation in the XORNet? What's your plan to implement this XORNet on the hardware side? And what information you need to print out when you have the Python GPU code?
I understand.
Any other question? If no question, we can stop today. I will post the requirement at the end of this week. Thank you very much.
Thank you.
If you have any question, please email me. Thank you.
Thank you.